Percolation is a widespread phenomenon that determines the physics of many disordered systems, such as random networks, nanomaterials, granular superconductors, or magnetic domains in perpendicular anisotropy materials. For example, as the temperature is lowered across the superconductivity transition in a disordered sample, nucleation of superconductivity occurs at random locations so that the resistance of the system decreases. A zero resistance state is finally reached when the first path of overlapping superconducting regions reaches one electrode from the other. This percolating cluster has fractal properties due to the existence of holes of all possible sizes. Percolation phenomena depend critically on the geometry of the underlying physical system. Recently, the concept of double percolation has been introduced in order to describe situations in which disorder occurs on a two-level scale, such as polymer blends or disordered high-temperature superconductors. In this kind of processes, two different length scales come into play, indicating that the physics of the system is dominated by two different disordered processes. Labyrinth domains in perpendicular magnetic anisotropy materials are a very interesting system in which double percolation effects could be found. Their physics are controlled by two independent random processes: reverse domain nucleation and reverse domain expansion. Their disordered structures can be described in terms of fractal geometry. An interesting feature of magnetic domains in perpendicular magnetic anisotropy materials is that their geometry can be easily tuned. By adjusting the magnetic history, you can switch from ordered parallel stripe configuration to disordered labyrinths. The question is now how to measure percolation effects across this disordered labyrinth structure. In our work, we have used hybrid superconducting ferromagnetic bilayers in which the domain structure of the ferromagnetic layer is imprinted in the superconductor due to the local stray field. For small magnetic domains with size comparable to superconducting coherence length, nucleation of superconductivity is favored above the reverse domains. This results in a network of superconductivity channels that percolate across the sample, with the same geometry as the underlying labyrinth magnetic domains. This has allowed us to study the change in the superconductivity phase boundary as the geometry of the percolation network is modified through magnetic history. In the fully percolated state, the upper critical field shows the characteristic temperature dependence of confined superconductivity on a fractal network. In summary, the disordered labyrinth domain structure of perpendicular magnetic anisotropy layers have been used to imprint a fractal geometry in the superconducting state of bilayers. Superconducting transitions display a characteristic percolative behavior with a niobium film broken up into a mixture of extended normal regions and islands of confined superconductivity. The distribution and size of these islands is controlled by a two-level percolation process. Firstly, by the random distribution of initial reverse nuclei determined by magnetic film history, and secondly, by the fractal expansion of each cluster of reverse domains resulting in a larger effective superconducting area. The dimensionality of upper critical fields, when domains adopt a labyrinth geometry, is characteristic of fractal superconducting networks.
My name is L Ruiz-Valdepeñas. I'm a graduate student at University Complutense of Madrid. This work has been done in collaboration with the following institutions: Universidad Complutense de Madrid, Universidad de Oviedo, Centro de Investigación en Nanomateriales y Nanotecnología e INDEA Nanociencia.